Good afternoon, AP Physics C. This is Miss O'Connell. I got a question about a homework problem from Chapter 1, so hopefully this helps a little bit. So in section 1.3 in your textbook, it talks about dimensional analysis, goes into, in the previous section, the prefixes for SI units, or technically we call them metric system units previously in regular physics. So here's just some background information in case you forget. I know that some of you have taken physics nearly 2 years ago. So a vector is a quantity with magnitude and direction. What we mean by magnitude is just a value, okay, and direction, especially in kinematics, is going to designate north, south, east, west. Sometimes you use a positive or a negative sign to denote a direction. And then dimensions are also part of that vector or scalar quantity. Before we get to dimension, a scalar is just a quantity with magnitude, meaning a value. It doesn't have direction, such as time. So time technically only moves in one direction that we know of or can observe right now. So we suggest that's a scalar quantity, meaning it doesn't have direction and only has a magnitude. Both scalar and vector quantities need dimensions in physics. It's kind of just a standard practice that we use dimensions to measure quantities. So a dimension, or commonly referred to as a unit, gives quantities in physics a context. So it determines whether that value corresponds with a length, a volume, a time, etc. Dimensions are typically denoted using a symbol, such as lowercase m for meters. So that should be familiar to you. Before I get to the example of looking at an equation and determining whether it's dimensionally consistent, let's just do a quick review of metric prefixes. So the most common prefixes that we convert in regular physics is kilo, centi, deci, milli. There were some times where we had to talk about micro. So in that electrostatics unit at the end of the year, we did microcoulombs. So we had to convert to micro. The most common units that we'll talk about in AP Physics C are nano, so 10 to the negative 9th, micro, 10 to the negative 6th, and then typical milli, centi, deci, kilo. We won't really talk about mega, giga, or tera that much. There might be an occasional time where you'll have to convert to that. But I haven't seen that on the AP exam thus far. Okay, so let's look at example 1. Let's say a car is traveling at 130 kilometers per hour. Find the velocity of the car in centimeters per second. Not the most ideal units, obviously, but this is just, practice in converting. So what we want to do is set up similar to a proportion. Okay, we're going to start out with the unit that we're given. So the car is traveling 130 kilometers per hour, so every hour it's going to travel 130 kilometers, assuming that the speed or the velocity is constant. We want centimeters per second. So from basic background knowledge, we know that in 1 kilometer we have 1,000 meters. So we need to multiply by technically 1, right? Because 1 kilometer is equal to 1,000 meters. We know that the kilometers need to be in the denominator because we need them to cancel out. And we'll have meters in the numerator. We need to go one step further because we still need centimeters. So we know that in 1 meter, there are 100 centimeters. Meters cancel out. We're left with centimeters in the numerator, which is the units that we want. One more step, we need to convert hours to seconds. We know that there are 60 minutes an hour. There are 60 seconds in a minute. So 60 times 60 will get 3,600 seconds in 1 hour. That's a horrible S. There we go, better. Hours are in the denominator, so they'll cancel out with the hours in the numerator. We'll be left with centimeters per second, which is the units that we were asked for. You want to multiply the numerator through, then divide by the denominator. So 130 times 1,000 times 100. Enter. Divided by 3,600. We will get 3,611.11 centimeters per second. Okay, so if you've previously taken AP Chemistry or you read the section in Chapter 1 about significant figures, you're probably thinking 130 has 2 significant figures. Why does our answer have, nearly double that? So it is true that significant figures are important, especially when we're talking about multiplying numbers in scientific notation. But on the AP exam, they're not going to take off points for using more significant figures than are needed. In physics, we want to make sure that our quantities are exact. So you do want to pay attention to significant figures, but you want enough figures so that if you had to use this number again in a different calculation, it wouldn't be completely inaccurate. So they would, however, take points off on the AP exam if you were to, be a little dramatic. You might make the grader angry if you, keep adding those ones in there. That's obviously a little ridiculous. But I'm going to say for the context of our class, you want at least 2 values after your decimal place, okay? Use your best judgment, but you don't want to, simplify this answer to just 3,600 centimeters per second because we need a little bit more figures than nearly just 2. Okay, so let's move on to dimensional analysis. So we'll do a 2-part example. Basically, if you're asked to determine if an equation is dimensionally consistent, it's just asking you to look at the units and determine whether the units make sense. So in physics, we could kind of figure out whether our answer was correct or whether we did the algebra correct if the unit we're left with made sense, right? So if you solve the problem, you know that you're looking for delta x, you're left with just meters, you know you did the algebra right. Or at least hopefully you did the algebra right. But when you're given no numbers and just an equation, which you will often be given in AP Physics C, you just want to take the equation and break it down into just units. You're kind of going to ignore the constants. So let's start with a nice example. Example 2, part A. We'll use one of the big 4, meaning the big 4 constant acceleration equations. So that's the v equals VL plus AT, v squared equals VO squared plus 2a delta x equals VO times t plus 1/2 AT squared. So we'll review all that stuff when we get back to school, but you should be familiar with it. So let's start off with equation 2. V squared equals VO squared plus 2 times a times delta x. Right, where v is our velocity final, or at a specific point, VO is our initial velocity, a is our acceleration, delta x is a displacement. Okay, so the units for velocity are meters per second. Write that quantity squared. That's going to be equal to the units, we're looking at only the units for velocity again, which are meters per second, again, quantity squared, plus 2. 2 is a constant, it doesn't have any units, so we can kind of ignore that for the sake of dimensional analysis. Acceleration is measured in meters per second squared. And displacement is measured in, sorry, that should be a multiplication sign, just meters. So let's simplify. We have meters squared over seconds squared is equal to meters squared over seconds squared plus, what happens here? We get meters squared over seconds squared. So the dimensions, or the units, on the left side of our equal sign compared to the right side of our equal sign are exactly the same. The units are the same. Okay, so that means the units are the same, the equation is dimensionally consistent. The units are consistent. So we're going to say that this equation is dimensionally consistent. Okay, so any proven equation that we use, or you have used in regular physics, is dimensionally consistent. The units on the left side of the equal sign should be equivalent to the units on the right side of the equal sign. Let's take a look at another example similar to the one on part B on homework problem number 9 in chapter 1. So let's say we have the equation y equals 4 meters times the sine of k times x, where we're told that k is a constant, and that constant is equal to 4 meters to the negative 1. Okay, so what that means, meters to the negative 1, anything to the negative 1 is going to technically be in the denominator. So meters to the negative 1 is 1 over meters. So what we're going to do is take this k, plug it into our original equation, and simplify it to see if our dimensions are consistent. So we have y equals 4 meters times the sine of 4, 1 over meters. Let's rewrite that to look a little nicer. Times x, right, that whole quantity. What happens here is that meters in the numerator, meters in the denominator, they cancel out. We're left with the equation y equals 4 times the sine of 4x. Technically, there are no units, so if there are no units on the left side, no units on the right side, that means that we're dimensionally consistent. Okay, so now give chapter 1, number 9 a try. Email me if you have any questions.